So we're right at the beginning of the binomial theorem topic, and I just wanted to take this time to give you a bit of an introduction, a bit of background to the binomial theorem, and to explore Pascal's triangle. So the idea of this is a little topic index, I suppose, and these three kind of topics here, these sections, Pascal's triangle, combinatorics, algebraic expansions, are just a bit of background knowledge. We're going to introduce a few ideas. The remaining three are the actual aspects of work that you're going to have to learn and will be examined upon. So let's have a look at the introduction here. So what's Pascal's triangle? What's all this about? What's the binomial theorem all about? So let's have a look, and we're going to introduce a little story later on. I see that the names haven't quite fitted into the screen here, so I'll move them. These are just some interesting characters in history. You've probably heard of some of them. Probably Blaise Pascal is the most famous of them all, and he's attributed with a lot of great mathematical developments, including the whole binomial theorem, and including the idea of what we call game theory. The other characters, Marin Mersenne was a monk, mathematical monk. Pierre de Fermat was a lawyer, actually, who was a bit of an amateur mathematician at the time, best known for Fermat's last theorem. And the Chevalier de Mere was just a rich aristocrat, and there's a little story I'll tell a wee bit later on, but I just wanted to throw out these guys. It's really worth exploring a bit of mathematical history while you learn some of these topics. There is some dice there, and that's going to play a good part in our story as well. So Pascal's triangle, if you haven't come across it, it's a really interesting number pattern, and it goes like this. It's easy to construct. First of all, you have to write down the number 1. And then we're going to make a triangle, hence the name. And we then, underneath the 1, we put. You can either make this triangle a right-angled triangle or effectively an isosceles triangle. I tend to make it isosceles. So in row 0 at the top, we've got a 1, and then we write down 2 1s. And every time you start, you write down a 1, but we're going to move it across. And then in between the 2 1s, we're going to add those two together and to make 2. And then we've got a 1 at the end. So we've always got a 1 at the beginning and at the end. But in between, where there are 2 numbers already in the row above, there's a 1 and a 2 we add, and we write down a 3 in between. The sum of the 2 numbers up above. 2 and 1 make 3, and then we've got a 1 at the end. Because effectively there's a 0 there, so 1 and 0 still make 1. And so we keep going. You can extend this infinitely, you'll be excited to know. 1 and 3 make 4, and 3 and 3 make 6, and 3 and 1 make 4. And then we've got a 1 at the end. And we can keep going. The next row has 1, and then we've got 5, 10, 6 and 4 is 10, 4 and 1 is 5, and then we've got a 1. So each row has 1 extra number in it. And you can see already some interesting things going on. There's obviously symmetry, an element of symmetry to it. There's all sorts of patterns. And I could keep going, but I've got one that I've already prepared, and there was a picture of one. Here, so here's a picture of Pascal's triangle down to effectively row 13. Okay. Now, there's a few properties that are really helpful to learn. First of all, we actually, I've already mentioned, I get rid of that we effectively number them from row 0. In other words, the first property is that the rows are numbered from row 0. Okay. The easiest way to remember the row number, if you're actually wanting to refer to row number, as I do, is effectively the row number is the second number in each row. So, for instance, row 2 is the number where it starts 1, 2. Row 4 will start 1, 4. Row 7 will start 1, 7. So that's the best way to think about the row number, is the second number in each row. Okay, so that's the first interesting property. We'll move that up here. Second interesting property is that in order to make it, you've already discovered that the sum of any 2 consecutive numbers is the value of the number below. That's how we've made it, so that's a fairly straightforward one. Property number 3, and this we're going to explore. I'll show a picture of it later on. I'll put it down here. The sum of each row is a power of 2. such that the sum of row n is 2 to the n. Okay, if you think about, for instance, row 1, 1 plus 1 is 2. And so we could say that the total there, let's put a total at the end here, the sum of that is 2. If you notice 1 and 2 and 1 for row 2, the sum is 4. The next one, 1 and 3 and 3 and 1 is 8. So we've always got, and then row 0 is just a 1, isn't it? So for instance, that's 2 to the power 0, that's 2 to the power 1, that's 2 to the power 2, 2 to the power 3, and so on. In other words, for row 0, when n is 0, it's 2 to the power 0. For row 3, the sum is 2 to the power 3. For row 10, we would have 2 to the power 10. That's a really interesting property. Well, I find it interesting. You might not. Okay, number 4, interesting fact. Number 4, column 2 is a set of triangular numbers. Column 2, it's a slightly kind of oblique column. I'm not going to use the word diagonal because I don't like it. But we'll highlight these in just a moment, so I'll come back to that one. And in number 5, it's just a little fact here that we're actually going, the whole point of introducing to this is that we're going to use these numbers in combinatorics and algebraic expansion. So we'll have a look at what this all means. But this is Pascal's triangle. So let's have a look at a couple of interesting things that we're going to learn from this. Here's combinatorics is something we're not going to really deal too much with. The only thing we're going to need is the idea of this capital C, the combinations function. You've maybe checked on your calculator before about something that's got an NCR and an NPR. You maybe never known what they're all about. Well, we're getting a chance to use at least one of these in this course. So combinatorics is when we look at combinations and countable numbers. There's a whole lot that we can get into, but all I'm going to say to you just now is the idea of combinations is the number of ways as you can choose a smaller number from a larger number. So n choose r is written n capital C R or just n over r, like a vector, like a kind of matrix vector. So we say n choose r. So 6C2 or 6 choose 2 is basically in a logical way of saying how many ways can you choose 2 people from 6. Okay, now you could sit and work that out in a bit of paper. Because if you could imagine if you had A, B, each person, 1, 2, 3, 4, 5, and 6, you can choose 1 and 2. You can choose 1 and 3 and so on. The combinations doesn't worry about the order of it. So 1 and 2 is the same as 2 and 1. So there are less combinations than what we call permutations. So what you need to do to get 6 choose 2, I want you to get your calculator and I want you to find the button that will say there'll be it might actually say NCR. That's probably what it says on your calculator. And if you find that button, what you would normally do is you'd press the 6 first and then the NCR button, and then you press 2. Or depending on your calculator, it might come up with the whole little boxes to fill in. But I'm going to let you find that on your own calculator. So on mine, if I do 6 and it's shift divide, I've got a Casio calculator, 6 shift divide will come up with a C, and then the number 2, press equals, and you get 15. So according to our calculator here, oops, my pen slipped. According to my calculator, here we go. Yeah, I didn't want to go back. According to my calculator, the answer is 15. Okay, get back up here. And that's all we need to do. CR 6 choose 2 is 15. So let's have a look here. Just use your calculator again and have a go at these ones here. So stop the video and then I'll put up the answers. Okay, so 3 choose 2, you should have the answer 3. 5 choose 3, we should have the answer 10. 8 choose 4, you should have the answer 70. And 11 choose 3, you should have the answer 165. So that's just a wee check to see you can actually use your calculator for this. Okay, so just keep them going, so bear with me. I know this is a bit of a long video. Interestingly though, what's the connection between that and Pascal's triangle? Well, if you notice that, let's go back to Pascal's triangle and see that if we wanted to see, we said that 3 choose 2 was 3. Well, if you happen to go to row 3, which is here, and if we have a look at the second, it says 2 here. What we don't do is we never count the first element here. That's always a kind of 0 element. So there's element 1 and there's element 2. In other words, the second element in the second number in row 3 is actually the number 3. Let's have a wee quick look at one of the other ones that we did. We said that 11 choose 3 is, what did we say 11 choose 3 was? Well, we said it was 165. Okay, so 11 choose 3, so let's go to row 11. Row 11 is down here. Oops, I've got things in the way, so we'll get them out of the way. We're at row 11, and where it's there, and if we don't count 1 and we go 1, 2, 3, ta-da, it's 165. And that's what we said it was from our calculator, that indeed 11 choose 3 was 165. So we've got a way of working it out with a calculator, and we've also got a way of working out the answers using Pascal's triangle. Okay, so bear with me. We're going on a little other journey here. So here's some algebraic expansions that you probably already are familiar with. I would normally say at this point, do them, okay? We're probably quite quick at doing x plus y squared because you might have a wee shortcut, or you might write them out twice beside each other. Whichever way, if you did it that way, we're going to be here for a while. It's not so bad, okay? You get x times x is x squared, x times y is xy, and then y times x is another xy, and then y times y is y squared. And if you simplify that, you get x squared plus 2xy plus y squared. Okay, so that's the answer to this first one here. If we're doing x plus y cubed, then you could say here x plus y cubed. If you're smart, you could just say it's x plus y multiplied by the answer x plus y squared, which we already know is x squared plus 2xy plus y squared, and you'd have to multiply this all out, okay? If you want to have a go at it, you could pause the video and just say, test yourself, because when you start getting on to x plus y to the 4 and x plus y to the 5, there's a lot of multiplication and there's a lot of places for making mistakes, okay? Suffice to say that I'll tell you what the answer is. The answer is x cubed plus 3 x squared y plus 3 xy squared plus y cubed. I just know that, okay? Not because I'm some kind of mathematical genius, but because I know the pattern. Okay, so what I'm going to do is I'm then going to write down x plus y to the power 4. And I'm going to write down what the answer is without doing any multiplying out, and you're going to be amazed. But I'm going to tell you that in a moment you're going to be able to do it yourself. So the answer here is x to the 4 plus 4 x cubed y plus 6 x squared y squared plus 4 x y cubed plus y to the 4. And without doing any multiplication, that's the full expansion of x plus y to the power 4. Okay, so what's going on here? What is happening? Well, you could see that in each case, x plus y squared, we start off with x squared, and then we've got an x. Just get my wee highlighter. So the x terms go x squared, x to the power 1, and then x to the power 0. Okay, the y terms go, there's no y term, y to the 0, and then y squared. So we've got decreasing powers, so increasing powers of, start again, decreasing powers of x from the top number, which is the same as the 2 here, and then we've got increasing powers of y. Simultaneously, and this is the amazing bit, if you notice that we've got effectively a 1 and a 2 and a 1. 1, 2, and 1 are our coefficients. With x plus y to the power 3, our coefficients are 1, 3, 3, 1. You recognise that. X plus y to the 4, 1, 4, 6, 4, 1. Okay, if you're not smiling now, I think you should just chuck this course right now. Okay, because here we have the numbers in all the different rows of Pascal's triangle. So if you're trying to do an expansion of x plus y to the power 5, all you need to know are the numbers in row 5 of Pascal's triangle that are going to form your actual coefficients. And then all you need to do is to start writing x to the 5 and then decreasing powers of x, and then you start multiplying by increasing powers of y, and you'll have your answer. So to summarize, this is what we're saying for any expansion, x plus y to the power n. The coefficients are in row n of Pascal's triangle. Powers of x decrease, powers of y increase. Therefore, just very quickly, because I know this has been going on a while, but hopefully if you can't cope with it in once, you can do it in installments. Here is the expansion. I'll show you what we're doing with x to the power, x plus y to the power 6. Well, what's row 6 of Pascal's triangle? Okay, let's just remind ourselves. If we flip back a couple of pages, row 6 is somewhere in the midst of all this mess here. 1, 6, 5, 20, 15, 6, and 1. Okay, there's row 6 there. You remember those numbers because I'll forget. 1, 6, 15, 20. So let's go for it. Let's write them down at the side. 1, 6, 15. Once you remember the first half, effectively, then the symmetry just repeats the other side around. So there's our number of terms. So what we do is we start off with a 1, of course. So it's going to be 1x to the power 6, which is the maximum. There's not going to be a y term. And then we add to that, our next term here is 6. So we've got 6, decrease the value of x to the 5. And then this is our first y term, because we had y to the 0 and now y to the power 1. And then the next term is going to be 15. Decrease the value of x and increase the power of y to 2. Plus 20, see what's going on here? X cubed, y cubed, plus 15, x squared, we're going down to x squared up to y to the 4, plus 6, x, y to the 5, plus 1, y to the 6. There's no x term there, and that's our full expansion of x plus y to the power 6. Okay, we could do the same with x plus y to the power 7, x plus y to the 8. I'm not going to just now because I've already been going on for long, but we can use the same principle in all of these. That's a really exciting connection, again, between an application, in this case multiplying out brackets, and Pascal's triangle. Okay, so we're going to have, I'm just giving you these things to make you go, wow, this is, I see the connections in all of these things. We're going to develop them later on. The last thing we're going to do before, two things. Okay, this is where Blaise Pascal came along, because there was a dice game going on, and between the Chevalier de Mer and a few of his friends, and he came up with a problem. They stopped a game of points. The problem of, it's not points, it's points. It's a French dice game, and they had this problem, and he wrote to Fermat, Pierre de Fermat, and said, what do you think? And Blaise Pascal got involved. So I'm just going to put the story up. You can pause it because it's interesting, and I'm just going to put the answer up, and you can see what their answer was. Okay, so this was actually the beginning of Pascal's development of kind of statistics and game theory, because it certainly wasn't a mathematical topic at the time, and a lot of it just stemmed from gambling. So, last thing we're going to have to do is look at just a few interesting pictures of Pascal's triangle, a few of the properties. We've already highlighted the fact that the sum of each row of Pascal's triangle is a power of 2. That's an interesting one. And as I mentioned before, this kind of third column here, 1, 3, 6, 10, 15, 21, 28 are triangular numbers. If you don't know what they are, look them up. I'm not going to explain to you just now, but there they are in all their glory. Here's another picture. Fibonacci numbers. Now they're a really interesting group, and you have to be a wee bit more creative to find them in Pascal's triangle. But if you were to take a slice through each of the rows in this angle, then you find Fibonacci numbers. Okay, somebody was very creative in finding them, but there they are. There's a hockey stick pattern, which is kind of self-explanatory. If you start from the edge and go down in that kind of sloping fashion between consecutive numbers, and then you do a turn in the opposite direction, the number that you get at the next number is actually the sum of all the ones that have come before. Now, that's a nice little pattern like that. The Hoggett-Hansel identity is if you take any number and then consider the 6 numbers around it, then basically the product of every other number is equal to the product of the remaining 3. So in other words, we're not thinking of the 10 in the middle, but in this case here, the 3 pink numbers multiply to the same value as the 3 yellow numbers, which is again an interesting connection. And that's basically it. We're going to go into the factorial operation in a moment. So that's a whole introduction to some of the aspects of the binomial theorem, particularly the idea of combinations and Pascal's triangle, and the fact that these numbers are in Pascal's triangle are going to form some really interesting mathematical work that we're going to go on to. So I hope that wasn't too boring for you. There's just a lot of stuff that I like to get across when we're dealing with the binomial theorem. Okay, so on to the next stuff once you get the hang of that.